All right, we are often interested in problems where we seek a solution of a differential equation so that it also satisfies a prescribed side conditions, that is, conditions that are imposed on an unknown function and its derivatives at a given number. On some interval containing that number, the problem of solving an nth order differential equation is subject to n side conditions specified at a given point. So in generic terms, kind of come in here and kind of do the whole point thing, we have an nth order differential. It's subject to some n number of terms in it. In order to solve an initial value problem, we just have to make sure we have enough initial conditions to match the type of derivative we're given. So if I'm given a first order linear differential, then I need at least one initial condition in order to solve that c constant that typically shows up. If I have a second order differential, then I need two initial values, one for the initial position and then one for the first derivative. If I have a third order differential, then I need three conditions, the initial, the first derivative, and the second derivative, etc. The value of y sub x and its first n minus 1 derivatives is called the nth order initial value problem. Oh, I messed that up. That's this up here. Sorry about that. All right, the values of y sub x and its n minus 1 derivatives at x naught, maybe some potential y value of x naught equals some y naught, or maybe the derivative up to the nth derivative, 1 degree less than the derivative that I'm given. So if I have a fifth degree differential, I need 4 initial conditions in order to solve that. All right, so the geometric interpretation of all of this is, and I'll kind of go through 2 cases here. So one, we have a linear first order differential and then a linear second order differential. And what we're specifically stating at this point is if it's a first order differential, so here we got first order and here we have a second order. In order to solve the initial value problem, I need to have a single condition, and in order to solve a second order differential equation, I need to have 2 conditions. And the specific ones that are stated below, again, these are in generic terms. So these are examples of first order and second order, respectively. And then you kind of see graphically, and this goes back to, in the last lesson, we talked about families of solutions. So those 2 different graphs would represent, this would be the first order on the left, and this would be an illustration of the second order on the right, where we're given enough information that we can essentially identify the particular curve that we are specifically looking for. And without those initial conditions, then any of those curves would be solutions of the differential equation. Alright, so the word's initial conditions are derived from the physical systems where independent variables is time and where the function of value at some given time corresponds to a value of y or a height, if we're talking maybe a physics problem. And then the y prime would represent velocity, again, if we're talking about that same distance problem. All right, so let's put our thinking caps on for a second. What function do we know from calculus is such that its first derivative is equivalent to itself? So don't think too hard about this one, but you take the derivative and you get the exact same thing, right? Okay, so let's say I let y equal e to the x. What's y prime? E to the x, right? What's y double prime? E to the x. So no matter how many times I take a derivative, we're looking at some form of e to the x. So let's have some fun with this for a second, and let's put it in sort of a generic sense. And so for some unknown initial condition, we'll call it c e to the x, where c is going to be defined by some particular choice of, something we're given to deal with initially. So let's add to it that we know that y of 0 happens to equal 3. Could we then at that point write a specific equation, a specific solution with that initial condition? And the answer is yeah, we can. We just evaluate y and x and then solve for c. So 3 equals c e to the 0, and e to the 0 is 1. So in this case, that would be 3. C is 3. So given the initial condition of y of 0 equals 3, I'm going to make sure I write on the screen here, then my equation then would be 3e to the x. Again, let's kind of play around with this, and let's change our initial conditions and see how that impacts things. So we have our general equation here, and let's say our initial condition is y of 1 equals -2. Meaning the ordered pair 1 comma -2 is considered part of the function. How would that change our value of c? How would that change our specific solution to that differential equation? Well, same thing we did a second ago. We're going to evaluate x and y. So here we got c to the first, right? Let's see. So that says -2 equals ce. So if I want to solve for c, I'm going to divide both sides by e. And I'm going to take advantage of some exponent rules here for a second, because that's a valid number. So -2e to the -1. So my specific differential equation with that new condition would look like this. So hopefully that gets a quick sense as to how initial conditions can impact the type of solution we have. So one question that we spent a lot of time addressing, or two questions actually, are the idea of existence and uniqueness. So does a differential equation actually have a solution? And do any of those solutions pass through a given point? And can we say specifically that that one solution that is the only solution through that given point? So we'll kind of do a quick thought experiment here. We'll kind of illustrate that. So let's consider, let me kind of make sure I got this up there. Let's consider a differential equation we kind of played with recently. So dy dx equals xy to the 1/2 power. And let's throw in the initial condition y of 0 equals 0. So will the following two differentials satisfy that? Now, this second one we played around with in the first lesson, and so we did find that that will satisfy that. As far as the form goes, we just need to confirm that if I put does y of 0 equals 0 in this case. So if I put a 0 in and I put 1/16, 0 to the 4th power, that in fact does say 0 equals 0. So that checks. But what about the equation y equals 0? Could that also work for us? And let's see. So we need we need y prime, which is 0, right? And so on the dy dx, that's 0. And then x times 0 to the 1/2 power is also equal to 0. So that checks and that checks. So both of those work. Kind of creates a problem because we have two different cases here, both going through the same initial point. Graphically, we can kind of do a quick comparison of these. So if we think back, what does y equals 0 look like? That's a flat line right there. make that a little bit thicker so we can see that. So it's a nice flat line through the origin. Right, and then what about 1/16 x to the fourth? Well, if you remember your college algebra graphing days, it looks kind of quadratic. It's a little bit thicker at the bottom end there. So it might come out looking something like this. And then the point, the initial value that we're given is at the origin. And so you can kind of see that, yeah, there is some overlap. There definitely is that interval of convergence around that. So there is an argument that for a brief period, both of those equations will satisfy that differential equation. So we'll spend a little bit of time honing in on that conversation and trying to come up with a stronger definition about, how do we guarantee there being a unique solution or not.